All right, I think we're ready to start. Close enough, anyway. So this is lecture one. Well, class one. I don't know if it will be a lecture so much, but it is lecture one for statics and strength of materials, engineering 220. So it's actually a combo class. So it's not just statics, even though most of the students call it statics. It's actually several different topics mixed together. Statics is one of those topics. And then there are strength of materials topics mixed in as well, which those are, statics might be the study of the forces that are applied to an object and how they interact with that object. And the strength of materials part is how does the object respond to those forces. So does it bend or twist or stretch or compress or do something like a break, fracture, something like that. So all of those things will be mixed in kind of concurrently. The general layout of the course is the first third or so maybe the first 3.5 weeks, they are axial based. So the forces are stretching on things or compressing things. And then the middle third, the forces are arranged in a way that the objects are bending. So like maybe a beam and it's bending. So it's like a curved shape. And then the last third is a couple of different things mixed together, but maybe the bigger topic in there is the torsion. So things are twisting. Maybe you've got some kind of force that would twist some object. And so that's the last third. There are 3 exams, one that covers basically that first third, one that covers that middle third, and then the last one kind of covers a little bit of everything. So it's not just torsion. There's a lot of different topics in there. The last exam is a little bit comprehensive, but it is mostly torsion, I would say. With these other topics, like there's some pressure vessels thrown in there. There's stress concentration factors. There's a couple of different things at the end. So what we're going to do is today we'll kind of go through the outline, what things are going to look like. We'll go in and do a couple of problems. The stuff we do today should be review. So it should be stuff that's not new. Maybe I've said something like a little bit differently than you've heard it before, but it should be all new, all old content, nothing really new. And we'll do some examples and things like that. Let's look at the textbook that we're going to use. I have it over here. So we're going to use this book. There's the name of it, Statics and Mechanics of Materials. This is the 2nd edition. It's actually a relatively old book. I'm not even sure what year. Mine is very old. Let's see if I can see the copyright on it. 2002, so like a 20-year-old book. And but it's still good. There aren't many books like this. There's probably a newer edition of this particular book, but there aren't many that combine statics and mechanics of materials. A lot of them either are just statics or maybe they combine statics and dynamics. But this is a book we'll use. We don't do a lot of content directly from the book. There are charts and tables and things like that we use from the book. The homework will actually be done in web work, so I'll show you that in a second. But the homework in the book is a nice practice set. So like the web work problems, you can work those, and then you can go find a similar problem in the chapter for the book and work that one as practice. But it's a good book. We will use it mainly for reference material. So we'll go in and we'll look at a chart or something like that in there. Let's look at our syllabus here. So here is the Moodle page. So we're using Moodle for this one. We haven't switched over to Canvas for this. So this one will be in Moodle. You should have access to this if you're taking the course for credit. And it is a 10-week, so the whole summer. August 10th is the last day of our class here. Actually, the last day we do anything is August 9th. You can kind of see the dates for the 3 exams, so go ahead. I don't plan on moving the exam dates unless there's some major reason that we have to. These other dates, the ones that are just labeled class 1, 2, 3, well, I guess class 1 is today, so we're not moving that one. Class 2, class whatever, those might move around a little bit as needed, but they shouldn't. This class does have an odd schedule. We meet on Monday, Wednesday, Thursday, so not Monday, Wednesday, Friday. That just has to do with the way university does summer hours. So even though we're online, I'm still following the university schedule. So Monday, Wednesday, Thursday at noon is when we'll actually do these streams. They'll stay up though, so you can watch the recording later if you want to go back and watch it, or if you missed it the first time, then you can do that. And like I said, the exams, so where's exam 1? June 22nd, exam 2, July 20th. On August 7th and 9th, there's 2 different types of exams there, so those are a little bit different. August 7th, let's say that you take exam 1 and it doesn't go very well. So it's kind of low, and you want to redo that one, or exam 2. So 1 or 2, you can take a new version. It won't be the exact same copy, but it'll be a new version of exam 1 or exam 2, and it will completely replace your old grade. Even if you did worse, hardly anybody ever does worse, and when they do, it's like a point or 2. Nobody ever really does significantly worse, but you can completely redo one of those exams. You don't have to redo either one, but you do have that. That's August 7th, so that's the Monday of the last week. And then August 9th, the Wednesday of the last week, is exam 3, and like I said, it is a comprehensive one. Let's see. Let's look in here. That's just, this is showing a playlist from a couple of years ago. I don't know exactly which one this goes to. I've got several playlists of this exact class or this exact course out on YouTube, so you can pick up one of the old ones. I do things differently every time, so generally the same topics, but like the examples will be different. So if you want to hear something explained again but not exactly the same, then you can look at one of those old ones. There's nothing in this announcements for them, but it's there. Here's how the grades work out. Let's see if we can get it to look at that. So there is a design project. So you're all scattered around everywhere. So some of you might actually be in town and you can collaborate, but I know some of you are not. So the design project is a little bit different in the summer when we're doing the online version, because normally what this would be is you create a design of maybe a truss, and you go in and laser cut it and physically build it, and you test this truss. That may not work when we're all scattered around. So what the design project ends up being is it ends up being a simulation. So we'll do the things in SolidWorks. I just saw a question: do we need a proctor, or can we take the test on Zoom? Either one. So on those exams, those all 4 exams, the redo and the 3 regular exams, you can either get a proctor if you can't meet during this time, and we can arrange that separately. But assuming you can meet during this time, the 12 to 150 time slot, then I'll send you a Zoom link, and you'll get your computer. They're in Moodle, the exams are, and you'll sit in front of that thing, turn on your webcam, and I'll watch all of y'all in Zoom for the exams. So the exams can be either way. You can have a proctor if you can't meet during the 12 to 150 time slot, but assuming you can, I think most people probably can, so most people will be in Zoom, but there could be some that are somewhere else. And we can arrange for that too. If particularly if it's out of that time slot, then we're going to have to figure out a proctor of some kind, and we can do that. We can do proctor you. You can do a proctoring service. So there's several different options. If you need that option, let me know so that we can figure out what you're going to end up doing. We've got some time to figure it out. Back on our grades here, you've got the homework. That's in web work. I've got web work pulled up right here. There will be a whole list of web work things. Now, some of these you're not going to, like a lot of these you won't actually see. These are all of them. I will assign the ones you actually need to do. Generally, it's going to be these that are labeled HW01, and then you'll have a homework 2, a homework 3, and so forth. You'll also have these OP. Those are optional. And so this OP1, those are all harder. They're a little bit harder problems. And they're all optional, so they don't actually count towards your homework grade. And the 1 set, so the 0-1 set, are all related to test 1. So you can go into OP01, and there's gotta log in. There's a whole bunch of them. There's 38 of these optional problems in OP01. And you can practice. You can use those as practice problems. You can use those as just nothing. You don't have to do them at all. If you do complete them, then they are worth a total of 3 extra points on your final grade if you did every one of them. Now, there's a whole bunch. There's an optional 1, there's an optional 2, and there's an optional 3, and each one have multitudes of problems in them. So you can get some extra credit, up to 3 total points on your final grade if you were somehow able to complete all of the optional problems. You will get a percentage of whatever you do complete. So if you do 1%, then you get 1% of those 3 extra points. Let's see, what else is about homework? Homework has days generally. The homeworks, the HWs, are we talk about something in class, and I assign the relevant homework, and you have a week to do it. The OP, I open those at the beginning, so there's OP01 is open now, and then after exam 1 is done, we'll open the second one. They're due on the exam date that they correspond to. So you've got those. So homework will be done in there. What else is in our syllabus here? These 2 lab assignments. So again, if we were in person on campus, then we would go down to one of the testing machines and we do some tensile testing and some 3-point bend testing. Since we are not there, then these become SolidWorks simulations. So in fact, let me add this little thing here. Let's see. Just so I can see where we're at. Put a little poll in the chat. Just to see, make sure we're good with SolidWorks. You don't have to use SolidWorks. You can use some other online. Onshape doesn't do simulations. You can use Fusion 360. At least I don't know if Onshape does simulations yet. So you could use another piece of software. The ones I'm going to show you how to do, though, are SolidWorks. And there's 2 of those. They're just 2.5% each. Moodle quizzes, if we looked, well, I've closed it right now, but if you look through the Moodle page, you'll see quiz 1, quiz 2, quiz 3, so forth. Those are kind of on your own. They're not during class time, and they'll just open. They'll stay open for about a week, and they will be examples of the simpler questions on the exams. So, but they will count as these Moodle quizzes. So each one of those, there's 5 of them. Each one of those will be 2%. And then you've got of exam 1 and exam 2. So whichever one you do worse on will count 15%. Whichever one of those, I need a parentheses there. Whichever one you do better on will be 25%. And then the final exam is also 25%. And again, that redo, you can redo and replace one of exam 1 or 2. Question in the chat is, design project is yourself or a partner? The labs, so the ones that have got 2 lab assignments, those are individual. The design project is group, as assuming we can make the group part work. That sometimes people are just, their schedules are too incompatible, like you're working an internship and you just don't have time to coordinate with another person. You can do the design project individually, but it's set up that you have a group of about 3 people. Even if you're remote from each other, you can still collaborate in Zoom or however you want to, email even. But it's set up to be a group project for the design project, the thing labeled design project here. But you can do it individually if you had to, just because of your schedule not working with anyone else. Let's see. Looks like most of you have the SolidWorks. That's good. If you don't have SolidWorks, then make sure by the time we get, this will be about halfway through the quarter probably. I'll do some SolidWorks before then, but the assignments for SolidWorks will be about halfway through. So make sure by then you either have gotten SolidWorks installed or you have an alternative. Maybe you just go and use Fusion 360 and figure out how to do the things yourself. They're not hard. They're not complicated. This is still a sophomore level class, so it's not like we're doing very advanced stuff on these simulations. It's just that we can't do them in person, so this is the next best thing. Let's see what else is in here on the... that was our grading. Oh, there's our textbook. This little folder here contains some of the charts, not everyone, but some of the charts from the book that we will use in class. So that could be useful. I'll probably reference those in class some, and I'll reference the book itself some, since I have it right here. And you'll also need some of those on exams. So the exams are in Moodle, but you still don't have access to like the internet or MathCAD or things like that. You do have to use regular old calculator, you know, to do math, to do your math in the exams. All right, I think that covers all of the syllabus stuff. Did I have any other attendance? I don't even think I had an attendance grade. Let me make sure. Since we're online, it's kind of awkward to do attendance, and the whole point of being online during the summer is that you're probably not available to be in person, because there is an in-person version of this course. So there's no attendance as far as grade goes. It does definitely help if you're part of the streams or whatever, but there's no attendance grade. Let's see. Oh, in this down, if we scroll further down here, there's some links to a Discord channel where you can ask questions, things like that about this course if you need to. I think my Zoom link is down there, and a scheduler where you can schedule some office hours. My email, all that kind of stuff is down further down on this page. Okay, I think if I don't see any new questions pop up in the chat, then I think we're probably good on syllabus type stuff. And we can move into the actual content. So today's content is 2D concurrent forces. So again, this should be review from at least from 122. So the engineering content in 122 is the beginning of this course. Maybe if you've taken physics 201, so that could overlap a little bit. Particularly in some of the vector type of things. We're going to use any of the examples and work that we use on the exams or that I do in here. We'll use resultants and X, Y, and Z components. So we won't use like vectors and IJK type of thing in this course, although I think the physics class did. All right, so I had put up a poll before we started the class, and just to test it, but it was a little question about, let's just read. I can't reuse it. I have to make it again. Let me type that in and just make sure that we're all kind of I just want to know where we're at. If I misspell stuff in the polls, you'll just have to be okay with that, because I have to type them on the fly. I can't preload them, or at least I don't know how to preload them. Maybe I can, I don't know. So I'm having to make them relatively simple. And all right, so there is our first little poll. Let's go over to here so that we can draw stuff. And let's just write down a couple of things for our 2D concurrent force system. Not sure what I think I hit a little light button there. Didn't mean to do that. All right, so 2D concurrent forces. Now let's write it in this. All right, so the 2D part, let's check on our poll. Lost my mouse. All right, yes, most people are getting the 707 answer, which is the correct answer for that. I'll leave that up for a little bit. All right, so 2D, we're going to do 3D next time, so that'll be Monday. But 2D just means we're working in a flat plane, you know, like the XY plane or something like that. Forces, we do have to make sure that we're talking about force vectors and not like scalars. So the difference between a scalar and a vector is that a vector is associated with a direction. So like a scalar could be area or mass or what's another scalar that I'm not thinking of? This stuff that doesn't a density, you know, something that's a measure, but it's not really a vector. It doesn't have a direction it's going in. Speed's a weird one where you think speed would be a vector, but speed itself is just like 10 miles per hour. And so it doesn't actually have any direction that it's going. It's just a speed. So speed is a scalar. If you want to talk about like a car moving in a certain direction, you would be talking about its velocity. So velocity would be a vector. Oh, wow. It automatically completes the poll for me. Good. Oh, no, that was the old one. Here we go. Let's end that one. And so forces that we're going to deal with are going to be vectors because we need to apply them to an object so that it can move around somewhere, except we're not moving in this course. This is statics and strict of materials. So the static part means that everything's in static equilibrium and we're not actually flying around somewhere. And then the other key word in here that we're starting with is this concurrent word. And so what that sets up a very particular set of force system. So for instance, a vector, so we've got a vector, it has a magnitude, we'll just put, I don't know, 10 newtons since I said that earlier, and it has a direction, so we'll put, that looks like maybe 40 degrees from horizontal, that'll be our x-axis, there's our y-axis. So that's a vector. It has a magnitude and it has a direction. Technically, it has one other thing too. It has a point of application. So that's useful because these vectors are going to be applied to some kind of objects. There's the magnitude. And then there's the direction. The direction won't always be some angle degrees. It could be given other ways, but for now it'll be this 40-degree thing. So those are our three things that we need to create a vector that we can use in our static calculations and in our strength of material calculations later. The concurrent force part of it, so the concurrent part, doesn't really apply when we just have one vector. So we need multiple vectors for them to both or three or all five or however many we have to all be concurrent. And what that concurrent means is, I want to define it this way and then we'll have to define some other stuff. So concurrent, it means that all lines of action intersect at a single point. So we have to define the line of action part. So line of action, so let's define that. if I take a force vector, so like the one that the 10 Newton force here, if I take that force vector and extend it in both directions, you know, the direction it's pointing and the direction it's pointing away from, that imaginary line, I usually draw it as a dotted line. That line is the line of action. So line of action is extend vector in both directions. So for our 10 Newton force, there's the actual vector. And then the line of action would be if I just kept going that way and I kept going that way. So that part is the line of action. Okay. Kind of didn't draw an eye in there. So it's pretty easy concept, but we do need to define these things. So that's the line of action. Went off the page a little bit. So for a force system to be concurrent, every vector that I have in the force system, all the lines of actions have to cross at a single point. So it would look something like, let's use our 10 Newton guy again. There's our 10 Newton force. And then let's put a, I don't know, an 8 Newton force over here. So ignore the 10 Newton that we drew previously, just these two. So the lines of action for this guy goes out here, you know, indefinitely. The 8 Newton goes out this way and this way. This point is where both of those two lines of actions, the 8 Newton and the 10 Newton line of action, where they intersect at. So both of my forces in this system intersect at one point, a single point. So the 8 and 10 are concurrent, at least concurrent when you're talking about that point, that where they intersect at. If we add another force, let's add one over here. We'll call this one 7 newtons, just to have a different number. It has a line of action, and it also intersects at that point. So now all three of these, the 8, the 7, and the 10, they're all concurrent. They're 2D because we're really just in this 2D plane. We're not in 3 dimensions currently. If I added another one, so if I add this guy, and we'll make it 6 newtons. It has a line of action, but it intersects here and here, not at that original point. So this one, not concurrent. The 6 Newton force, you can't just ignore that one. So you have to, if this is our force system, the 8, the 6, the 7, and the 10, if all 4 of those are part of our force system, then we do have to treat this system as non-concurrent. And we'll do that later in the quarter, so not yet. But the assuming we don't have that 6 Newton force, and we only had the 8, 7, and 10, then we can treat that as a concurrent force system, which is what we're going to do today. I am recording the stream also, just by the way, so that if it freezes up on us again, then I can keep going and post the rest of the video. And you can watch it just as a recording. All right, let's see. We talked about all of this. Talked about that. Oh, yes, equilibrium. So 2D concurrent force system, so that's good. We also want to have the idea of equilibrium in here, static equilibrium. So let me go to here, and let's add in that we're also talking about static equilibrium. So if you remember Newton's 3 laws of motion, so Newton's 3 laws of motion. one you could summarize as the law of inertia. So it would be something, body at rest tends to stay at rest, body at motion tends to stay at motion, unless acted on by an outside force. So we'll just call that inertia. That's not really what we're interested in today, because, or at least in this course even, because we're not really talking about inertia. Two is sort of what we're interested in today. So that one would be acceleration. And the thing about this is that you could summarize this law with F equals ma, right? And it's the one where the acceleration of an object is directly proportional to the mass or the force of the object, or the force acting on the object, and inversely proportional to the mass, which equates to F equals ma. The thing about static equilibrium, so we'll say in statics, that acceleration is 0. So that makes this equation kind of interesting, because then it says F equals mass times 0, which says F equals 0. So that would be true if you didn't have any forces at all acting on something. Then yeah, there would be 0 forces and 0, it'd be in static equilibrium because there would be nothing acting on it. But we're going to write this a little bit differently, and we're going to say that the summation of forces equals 0. So the net effect of all the forces acting on an object equals 0. So that's static equilibrium. And we'll actually break it out a little bit more than that even, and we'll say that, well, yes, the net effect of all the forces acting on an object, if the net of them, so if you add them all together as vectors, then if they equal 0, then it's in equilibrium. But again, we're not using the vector notation, the IJK, in this course, so we're going to write this equation as 3, and then we'll add another one later. 3 separate equations, which are the summation of all the forces in the x direction equals 0. So if I take all the x components, that was kind of our little chat quiz earlier on. So if I take all of them, then they will add to 0 in the x direction. Summation of forces in the y direction equals 0. And then summation of forces in the z direction equals 0. So x, y, and z, they all add to 0 independently. So all the x components will add to 0, all the y components will add to 0, and all the z components will add to 0. Now, go ahead and do the third law, because it kind of matters too in here, and it's the one that has to do with reactions. So the reactions being, for every action there's an equal and opposite reaction. That will be important, maybe not as important today, but it will be important later on. So we've got our three laws of Newton's laws of motion. Mainly looking at the second one, where in our static equilibrium setup, the acceleration is 0 because we're not accelerating in statics. And then we can take that and apply it to F equals ma and pull out our 3 equilibrium equations right here. And then, like I said, once we're in a non-concurrent force system, later on in the quarter, we'll add a 4th equation that we will need. One other thing we need is this idea of free body diagrams. So I'm noticing that the thing froze up, so we'll just keep going this way and I'll post it later. So for free body diagrams, what we're going to do is this is it's important for statics, mechanics, materials, and all of these types of things, because what we're doing here is, you know how every different type of engineering, so chemical or electrical or mechanical or civil, they all have these particular drawings that go with trying to understand a problem. So for electrical engineering, you have a circuit diagram with resistors and capacitors and all that in it, and different things like that. Well, the free body diagrams are those illustrations, but they're not just like pictures. They are meant to convey information about the problem. They're the things for statics and mechanics, and they have a couple of rules. And I think I will probably let's write out the rules, or let's write out a version of the rules. You can have your own version of the rules, but the whole idea for a free body diagram is that you have created a free body. So the free part means that it's not attached to anything. It is floating out in space, and then I can apply all of the things that were acting on this body to this diagram and analyze it. So step one, if you're trying to create a free body diagram, is to identify the object. So the object, and let me put in parentheses here, S, because it could be that the body that goes into your free body diagram is a single body, like a pin, or it could be a piece of the pin, like maybe it's just a button on the pin, or maybe it is a whole bunch of objects assembled into like a machine or a frame or a truss or something like that. And so you have to identify what it is that you're interested in. So for us early on, it's going to be pretty direct on how to identify the body. It's the thing that we're looking at, and it's kind of already isolated. But that's step one, is to go and identify the body. You can't really do this wrong, like, because you can choose whatever body you want, but you could choose one that doesn't lead you as quickly to the solution you're trying to get to. So it is important to identify the correct body, but you can't actually do it wrong, because you can always create a free body diagram correctly. It just may not be the one that you most need. So that's step one, identify the body and isolate it. So I'll actually put step two as isolate that body. So isolate it means like you're conceptually taking it away from all the things that it's touching in the real world, and you're putting them on the paper so that you can draw all those connections. So if I were isolating the pin here, I'd have to take my, I can't do it, because I have to take my hand away. I have to put my other one on there. But I have to take my hand away, and everywhere my hand was touching it, I have to replace that contact with a force. So I'm going to have to, as I isolate the body, you might even think about like you're outlining it and cutting it out and then putting it on your paper. Then I want to draw that body. And you don't have to be an artistic drawing. Sometimes the body that you draw is nothing but a dot. You know, it's just a point, and that's replacing the whole thing. That's sometimes useful just to make things simpler. Generally, I like to draw something that looks roughly like the body itself, but I don't always do that. Sometimes it is just a dot. It's just to represent the thing, the free body. So once you've got that, step 4 is you need to go in and you need to be able to identify all those forces. Remember I said that my fingers were touching the pen or whatever. So you need to identify the forces. So forces could be contact. So I'm touching the pen It could be weight, so the pin has a certain weight, gravity's pulling it down. It could be friction, so there's something that I'm trying to move and there's a frictional force resisting its movement. It could be a wind load of some kind pushing on a sign. All these different forces that once I took the body out of the real world and put it on my paper, I have to replace all those forces. Some of them you can ignore, like they're small enough that they don't actually affect anything. So maybe the wind, I've got a little fan sitting over here, the fan blowing on this pin does have like an effect, but it's so tiny that I can ignore that one. But if I had a big billboard sign on the side of the interstate and there's cars going by it all the time, there probably is a significant wind load that I have to deal with on that. You've driven past, like after a storm or maybe a tornado or a hurricane, and seen the signs completely knocked down just from a wind load. So you have to make sure that you understand the different contact forces and weights and everything, which ones are important and which ones you can ignore. In our course, I don't know, very rarely will I give you any that you can just ignore. Any forces that it's pretty well laid out on which ones you need to apply. You just need to figure out how to apply them. And we'll talk about that a little bit later. Once I've identified all the relevant forces, so the important ones, and figured out there's some that I don't need to worry about, now I need to represent those forces on the body as vectors, like on my picture. So, like that. So I might have to draw arrows, kind of like these guys, acting on that body. And for now, actually just for today, well, a couple of days anyway, all these forces are going to be concurrent. So they'll all end up meeting at some point somewhere. Let's see, what would I do after that? After I've drawn the forces, I need to label them, and that includes their magnitude and direction. So magnitude and direction of those forces. And then just to clean it up, I would probably need to put all of this, and I might have, if I were drawing this out, I probably did this step earlier, but I'm writing it down and it's the last step. But apply a coordinate system, like a X, Y, and maybe Z if we're in three-dimensional. Okay, so those 7 steps, mostly in this order. Again, I might draw the coordinate system a little bit earlier when I do this other times, but that's more or less the right order. Will get you a free body diagram. All right, so I think, let's see where we're at on time. Yeah, I think what I'll do now is I will go in and let's do some examples. So let's see, I had some worked out I wanted to work on. All right, so here's one we're just calculating resultants. So we're not really even talking about equilibrium right now. So let's make some room here, and let's get our little block. So we got this little block, and it's sitting on the ground somewhere, and we've got 2 things pulling on it. So let's say that this is, on the ground, and it's not moving. So we're not in a dynamic situation. We're in a static situation. So I've got one guy that's got a rope attached to this thing. Maybe he's got a little eye bolt in it over here, and he's got a rope, and he's pulling, let's see, I said 50 newtons, and that angle that he's pulling at from horizontal is, I think I said 30, yes, 30 degrees. Okay. And then that's not enough, so we've got another guy, and he has his own rope. Maybe he's got a machine or something, because he's pulling more. He's pulling 100 newtons. Whoops. That should be 100 newtons. His angle is 60 degrees from horizontal. So like that. So now this one, we do have the idea that this block is sitting on the ground, and there's some kind of friction force between it. And so if we look at it from that point of view, we don't have a concurrent force system. But what I'm going to do is I'm going to look at just this little guy. Just the little eye bolt that these this cable and the block are connected to. So from that point of view, if I were to enlarge that, let's look at our step one, right? Step one is identify the object. The object could be the whole block, but then the block's on the ground and the ground's acting on the block, and I've got these other forces, so I'm not going to worry about that. So I'm going to say the object is this little eye bolt that the block is connected to and the two ropes are connected to. Okay, I'm going to isolate that body. That was me drawing the little dots around it, so I kind of isolated it on the picture here. Draw that body. Now, a lot of people will think this thing that we're looking at right now is the free body diagram, but this is more like a sketch of the scenario or something. It's not the free body diagram because it's not free. It's connected to the ground. So I'm going to actually take and draw a bigger picture of just this eye bolt. So it would look something like this. And then, you know, it's connected to the block over there. Maybe it's screwed into it, or maybe it was made in part of it. I don't know. So there's my eye bolt. What's it say to do? That was drawing the body. Identify the forces. So the important forces to me are the 100 newtons and the 50 newtons, and then there is also some kind of reaction force. I don't know what it is, but there's some kind of reaction that the bolt is attached to the block. So the eye bolt is attached to the concrete block. There's some reaction there. I don't really know much about it, but I know that there's something there. So I need to identify those. There were 3 of them. Represent these, all right? So I'm going to put one force right there. 50 newtons at 30 degrees. Let's go ahead and put our coordinate system. So see, sometimes it's better to put your coordinate system in early than saving it to the end. So there's that force. Then there is, I'm going to draw this one longer. Technically the vectors should be scaled. Their length should be scaled to their magnitude, but I don't have room for that, so we're just going to do it a little bit longer than the 50 instead of twice as long. And then this guy is 60 degrees. And then there's this other force that I don't really know. I'm just going to put it, it looks like it, if I were it, it's doing something like this. I don't know, something like that. But I probably, let me erase that part. Let's look at just the bolt, the circle part of the bolt. So this is what I would call the resultant. and it has some angle. I don't know what. I'll just call it theta. So it has some angle. So this, what I can do here is I could treat this as an equilibrium problem. We're not really ready for equilibrium. What I want to do is I just want to calculate the resultant of these two. So basically, how do I add the 50 Newton force and the 100 Newton force? I can't just add them together and call them 150 because they're not in the same direction. They're kind of in the same direction, but they're not in the same line of action. If they're in the same line of action, I can just add them together, 100 plus 50. But since these are not in the same direction, I have to combine them together somewhere. So how I'm going to do that goes back to here with our summation of forces in X and Y. Kind of goes back to that. Each one of these forces has an X component and a Y component. And I'm going to say that I can calculate let's just do the X components. So the resultant's X component, so I'm using R for resultant and X, subscript X, as saying that that is the resultant's X component, is equal to the 50 newtons times the X component of the 50 newtons. So if you don't remember how to do the X and Y components, you're going to need to go back and review some sine and cosine and maybe even tangent. That if you don't remember how to do that part, then give me some emails or something like that so I can go back and kind of help you with that. But I'm assuming you remember how to do that. In this case, the 50 Newton X component is 50 newtons times 30, or well, not times 30, I can't do it, times cosine of 30 degrees. So basically that's creating this that vector right there. So that guy is 50 newtons times cosine of 30 degrees. And then the 100 newtons also pointing to the right, so it's plus. They're both going in my positive X direction. 100 newtons times cosine of 60 degrees. Now, don't get in the habit of, oh, I'm doing X's, I need to do cosines. Sometimes you need to use cosines, but that's not a 100% true all the time. So sometimes you might need to use sines. So you need to remember the definition of cosine and sine. So cosine is the adjacent side over the hypotenuse, and sine is the opposite side over the hypotenuse. So you do have to remember those definitions. And tangents, opposite over adjacent, if you need that one. Okay. We can add this up. Let's see. Let me get my calculator. Actually, I wrote it down over here, didn't I? I think it's 93.3, but let's check. Let me check my calculator here. 50 cosine of 30. Oh, make sure you're in degree mode. You know, you can, like if you're in MathCAD, possibly doing this. I could write these out in MathCAD. It will assume when you wrote cosine of 30 that means 30 radians. So make sure you're in degree mode wherever you're solving this thing, if you're writing degrees down. So this first term is 43.3 plus 100 newtons times cosine of 60, 93.3. So what this says is that if I were to add the 50 Newton and the 100 Newton force together, then the resultant, so the resulting single vector, would have an X component that's 93.3 newtons. So if I drew an arrow just in the horizontal direction, it would be 93.3 newtons long. We can also do the Y. So the Y component of the 50 newtons would be 50 times sine of 30 degrees. It's pointing up because both the 50 and the 100, they both are pointing upwards. and to the right. So they're both positive here. We'll do some in a minute that are not. All right. So 50 times sine of 30 is 25, plus 100 times sine of 60. Total is 111 newtons, 111.6 newtons. So those two, now when I drew my picture up here, I drew the resultant going to the left and downwards. That's I probably shouldn't have said that as the resultant, now that I think about it. That should be the reaction. It's kind of the opposite of the resultant. So the same magnitude but opposite direction. So the actual resultant would be, to get the magnitude R, you would do Pythagorean theorem. So a squared plus b squared equals c squared. In this case, rx squared plus ry squared equals r squared. So r equals the square root of rx squared plus ry squared. Whoops. So 93.3 newtons squared plus 111.6 newtons squared is square root of that. Let's see. Hold on. Square root. Where's the square root on here? Well, I guess I could raise it to... Oh, there it is. 145.46. Oh, this brings up a point. So the actual answer in my calculator, 145.4628819 newtons. So clearly that's too many decimal points. So you have to decide, where do you cut off the decimal points. You can use the significant figures, but generally in engineering, what you do is you cut them off where you think you can measure down to accurately. So in this setting, can you possibly measure millionths of a newton? Probably not. So if I were measuring this, I'd probably have like a little fish scale type of device, and it probably gives me tenths of newtons, maybe hundredths of newtons. And so what I would do here is, if I wanted to be, more precise, I guess, then I would round these off at 0.46, but probably I'm just going to round this off at 0.5 newtons. And that's fine. On the exams, they're set up in a way to where rounding at that level, a decimal place or 2 decimal places, is fine. There are a couple of calculations where we're calculating very, very tiny numbers, and those you have to have more decimals because a lot of them are zeros, right? So in this case, I would say that 145.5 is good, 145.46 is good, 145.463 is probably getting a little extreme, but it'd be okay as far as writing the number down. So like I said earlier, I can't just add 100 newtons and 50 newtons together and get 150 newtons. I actually get 145.5 newtons because they're not in the same direction. They're in 2 different lines of action. To figure out the angle that they're acting at, you just do theta equals inverse tangent of ry over rx. So inverse tangent of ry was 111.6 divided by rx 93.3. So that is 111.6 divided by 93.3. Inverse tangent of that is 50 degrees, 50.1 degrees. and that also makes sense. It is kind of between the 30 and 60. They're both moving in sort of the same direction, so they sort of add together and average out the angle, sort of. They're not the same magnitude, not the same angle, so it's not exactly the average of 60 and 30, but 50.1 degrees. Sometimes you have to be careful with this to make sure that the number you calculated is in the correct quadrant 1, 2, 3, or 4 of our coordinate system here. This one, Rx and Ry are both positive. That makes it quadrant 1, which the 50 degrees is in quadrant 1. Sometimes you have to add 90 or 180 or 270 even, depending on what kind of set of X and Y components you have. Now we did this with just 2 forces, the 50 and the 100. I drew the reaction on there, but that's really not one of the forces that we were calculating. That was just kind of showing that there's something holding this ring stationary, and it's this thing I called reaction. The reaction is the resultant, but in the opposite direction. But this process works no matter how many forces you have applied. So it's not just good for 2. You end up with 2 resultant components, X and Y. You add all the X components for all the forces together, all the Y components for all the forces, and that will create the resultant, which may or may not be an equilibrium situation. So, for instance, our resultant is 145.5 newtons at, 50.1 degrees. If I don't have the reaction that's exactly opposite of this resultant, then I'm not in static equilibrium. So assuming, because we're in a class called statics, assuming that this reaction that I've got drawn here is exactly opposite of this resultant, then I do have a static equilibrium situation. All right, let's see, we've got time to do some others. Let's see, I wrote down that one. Oh, this, while I'm looking at my notes here, doing this is probably one of the, not the easiest, but a 2-star problem or so on the exam. So the easiest thing you would have to do, we didn't even, well, kind of like, remember when I showed this and I put in the chat to calculate a Y component of this? That would be like a 1-star problem. The simplest that we'll have. You'll have some of those on the exam, not very many, but there'll be some just to make sure that you have the very basics down. Something like this is still on the simple side. All you're doing is calculating the resultant of 2 forces. So that's maybe like slightly harder than the other one. But you'll have some of these on the exam. Let's do something. Let's do something a little bit more than that. If I have one written down here. This one, well, that's more of just a, well, let's see. This one's slightly more complicated, I guess, but it's not much more. I don't know if I want to bother with it. Oh, what about this one? All right, we'll do this one. All right. And then that'll probably be enough for today. All right, let's get a new area here. So we have a spaceship. A little spaceship guy. And let's see. Actually, he needs to go the other way, doesn't he? Let's rotate him. There. All right. So, got this spaceship. He's in outer space, so there's no gravity or anything like that. He just has these thrusters. Kind of can see the 2 different little thrusters there. He's got those 2 things. He actually has a third one that we can't see that kind of keeps everything in balance. And what we've got is we've got if I were to draw the direction, the vector for these two thrusters that look like they're on here, he's got one. We'll call that F1. It's coming out maybe like this. I know the picture doesn't look like that, but that's what I wrote down, so it's fine. Let's put our kind of center. Okay, and this will be 30 degrees. And this other one over here is coming out, and its vector ends up kind of like this. I'm having to force them to be concurrent, so I probably should have put them a little bit lower, but it's fine. It's fine. 100 and just 100 newtons. And this one is 120 degrees. Okay. And then there's a third one that is maintaining an equilibrium. So there's some other force that we can't see that, but there's something maybe over here that is maintaining the equilibrium. We'll call that F3. So this one's F1 and this one is F2. And this third force is maintaining our spacecraft perfectly still. So that means it's in equilibrium. So it's in equilibrium out in space somewhere. There's no gravitational forces acting on it. It's just these three forces that are maintaining it in its position. Also, a lot of these problems we have to, oversimplify to make them stuff we can work on. So don't think too deeply about these things. It's just what we're showing you as far as these. You'll get, as you move through the curriculum, you'll get to do more thinking about these problems. So what we want to know is, what is the magnitude and direction of F3 in order to maintain equilibrium? So this will be given that stuff in our diagram. We want to find, make sure I'm still got the right stuff on the screen. Yep. We want to find F3 such that the craft is in equilibrium. Okay. All right. So we need to do a similar process to what we did before, and we can approach it a couple of different ways. What I'm going to do here is I'm going to go back to these equations right here. These are equilibrium equations. So I'm going to go back to those, and we don't have a z, so even though we're in space and it's technically 3D, we're looking at this as if it's 2D. And so we've got just our x and y equations, and I'm going to write those two equations for this system. Now, we've kind of already drawn our free body diagram, so we can start with this, I suppose. So summation of forces in the x direction equals 0. So the little sigma there is our summation, and this means to take all the force vectors, so I got 3 of them, F1, F2, and F3, and take only their x components, add them together, that's the summation, and they have to add to 0. If they don't add to 0, that means my spacecraft is moving in the x direction somewhere, and it's not doing that, so they have to add to 0. So let's look at F1. It has 50 newtons, cosine 30 degrees, Oh, this next part's good. So let me put that down. Here you can make an easy mistake on the. I'm looking at F2. It says 100 newtons, and then it's got 120 degrees measured from the x-axis. So I could do times cosine of 120 degrees, but then I have to decide, do I put a plus or a minus in here? And so what you could do is you look at this and like, oh, well, F2 is pointing to the left. That's in my negative x direction, right? If I, had this axis, that would be my negative x direction. So it's pointing in there, and I put a minus sign. But if you go to your calculator and actually do, you actually do the math for it. So let's get off of there. So if I go in here, where you at? And what is it? 100 times the cosine of 120. The answer I'm going to get already, it's negative 50. So it already has a negative sign in it. And if I go and put this negative sign, whoops, wrong one. There. This negative sign. If I put that negative sign in there, and then this number is negative 50, I've got two negatives and they end up being a positive. So you have to be careful how you go about putting in the forces that are not in quadrant 1. So what I usually do is I usually look at assign the arrow based on the direction of the force. So in this case, I'd give it a negative. But then instead of doing cosine of 120, I would probably do cosine of that degree. Or, well, I should do sine of that degree. So you just have to be careful on how you go about doing that. Make sure you don't do a double negative somewhere. So what in our case, since I've measured the 120, since I measured that, then this is actually plus. So that plus 100 newtons times cosine of 120. Then I've got this one. Its angle is that whole big thing there, theta. Now if I measure that theta from x, the positive x direction, then I can use plus F3, I don't know its magnitude, times cosine theta equals 0. So those three x components have to add to 0, or else this guy's moving. Oops, can't get him to move. It's moving in the x direction. There he goes. It's moving this way or that way, depending on if it's negative or if it's positive. Which I said it was in static equilibrium up here, so it's not moving in any direction. I can't solve this equation though because there's two unknowns, F3 and theta, so I have to write more equations. So the other equation I have is similar. Summation of forces in the y direction equals 0. And it's going to have the same issue where I've got F3 pointing down, but I've got the cosine of whatever that angle theta is, or well, the sine of it, and it's wrapping around multiple quadrants. So what I'm going to do is I'm going to do 50 newtons times sine of 30. That one's pretty straightforward. I'm going to do plus 100 newtons times sine of 120. And then I'm going to do plus F3 times sine of theta. So now I've got two equations with the same two unknowns in them. F3 is unknown in both equations, and theta is unknown in both equations. So at that point, I have to have some way to solve simultaneous equations. So you'll have your calculator, so you can have that. On the exam, these will not be, the ones where you have to do simultaneous equations will not be terribly complicated. I think I will throw this guy into MathCAD and see what comes out. So let's go over to the MathCAD real quick. So we need a solve block, don't we? So we've got F3, we'll give it a value of 1 Newton, and we've got theta has a value of 1 degree, we'll say. All right, and our equations that we're actually going to put in here are, let me see if I can get it all on the screen so I can see it. 50, oh, well, yeah, we can do that. 50 newtons times cosine of 30 degrees. With MathCAD, you have to put those DEG in there, or else it's going to think that's radians. Plus 100 newtons times cosine of, it was 120 degrees. Plus F3 times cosine of theta. Okay, that's one equation. Oh, well, hold on. Control equals, whoop. Control equals, to make it a symbolic equal, 0. The other equation, 50 newtons times sine of 30 degrees plus 100 newtons times the sine of 120 degrees plus F3 times the sine theta equals 0. So answer equals, I think I do find F3 comma theta. It found something. Answers equal. All right, so it gave us our 111.8 newtons, and then it gave us negative 1.5. So it did put that in radians. Angle equals negative 1.511, that'd be radians. Angle equals how many degrees? Negative 86.574 degrees. We have to interpret what that negative 86 degrees means. So that's going to put it in quadrant 3, measured from the negative x-axis. So the light went off. So what that would be in our picture. If I go back to our picture, we have F3 was, oh, I forgot, 111.8. So let's write these down before I forget them. F3 equals 111.8 newtons. Theta equals negative 86.6 degrees, we'll say. So if on our picture up here, that's this angle. That angle would be 86.6 degrees. And F3 would be 111.8 newtons. So in your process, you won't be able to do MathCAD on your exams. Obviously, you can use MathCAD for all the homework if you want to, but you do need a procedure, whether it's a calculator or just going into these equations by hand and you can actually add all of these. These are just constants. You can add those together and you can solve this by substitution or elimination or whatever. So you need a process where you're going to solve simultaneous equations. So I would recommend finding your calculator and finding the user's manual or looking it up online and seeing how your calculator can solve simultaneous equations. Monday, when we do 3D forces, I'll show you a way that any calculator, well, most any calculator can do simultaneous equations with matrices, but we'll do that on Monday. I don't want to do it just here for these 2D problems. But for 3D problems, you have 3 simultaneous equations to solve. And we'll look at how to do that with a matrix or multiple matrices. All right. I think that is probably enough for today. make sure you start working on homework 1, and make sure that you've got SolidWorks. Eventually, you've got some time to work on SolidWorks, but somewhere in maybe a month or so, you probably should have something like SolidWorks working, either that or Fusion 360, something where you can run a simulation, a static simulation. Let's see. I think that is all of what we need to cover today. If you have any questions, let me know.